Geotrig, lesson 25. We're going to talk about age problems and rate problems. So we're going to talk about age problems first. And there's something we need to know about age. Your current age is your age as of today. So let's talk about my age, Konchak's age. If I wanted to know today's age, it would be K years old, okay, for Konchak. Okay? And if I wanted to talk about 1 year ago, and I don't tell you how old I am, 1 year ago would be my current age minus 1. 10 years ago would be my age minus 10. 5 years from now, K plus 5. So you're getting it, it's all based off of today's age, right? That's how we're going to have to do our problems. And the problem that we're going to do, or the problems we are going to have to do, sometimes talk about 2 people currently, or 2 people 5 years ago, or 5 years from now. It also can link someone's current age compared to someone else's past or future age. Or it could also go for someone's past age and another person's future age. So there could be multiple connections, but here's the thing. Again, they're all connected back to the idea of your age today or their age today. Okay? So everything goes back to that. So our first problem, we have to write 2 equations with 2 unknowns, sometimes 1 equation, 1 unknown. That's how it works. 10 years ago, Tommy was twice as old as Patricia. 5 years from now, Tommy will be 10 years older than Patricia. How old are they both now? So what we need to do is we need to establish what variables we're going to use. And so I propose, when you do problems like this, stick with the letters of the first name if you can. So, T is Tommy's age, right? His current age. That means P will be Pat's age. Okay? We got Tommy's age, Pat's age, P, and T. That first sentence is the first equation. What is it? 10 years ago, Tommy was twice as old as Patricia. T minus 10. Tom's age. Patricia's age. Are they equal? No. Tommy is twice as old as Patricia. Where's the 2 in front of? P minus 10. Because Tommy is twice as old as Patricia, so if you know Patricia's age, you can multiply by 2, yeah? That was 10 years ago. 5 years from now, 5 years from now, what? T plus 5 and P plus 5. Are they the same? Because they're both from now, 5 years from now. In the future, Tommy will be 10 years older than Patricia. So this is kind of placing them both in the future 10 years from now. Or 5 years from now, sorry. Just like the first sentence placed the time 10 years ago. We're all basing it off of today. Tommy will be 10 years older than Patricia. So someone has to have plus 10, right? Who gets the plus 10? The P plus 5 or the T plus 5?
P.
Who's older than who?
Tommy's older than Patricia.
Tommy's older than Patricia by how much? So to make them equal, Patricia needs to be 10 years older, right? Do you have two equations and two unknowns?
Two equations, two unknowns.
So can you solve for P and T? So do it. I'm going to pause the video. You guys should be able to handle this. Obviously, the first thing everybody did was distribute the 2 and then gather the like terms on the second equation. So T minus 10, don't need parentheses, equals 2P minus 20, and T plus 5 equals P plus 15.
Plus 15, yep.
I don't necessarily know if I like it like this. So, do you notice that it's kind of like our X and Y systems? And so therefore I can kind of put them in standard form. Bring the T's and the P's on the same side, numbers on the other. I'm going to bring the variables to the left, keep our numbers on the right. Is that okay? So on our first equation, T minus 2P equals negative 10. Did everybody see what I did? I subtracted 2P from both sides and then added 10 to both sides. Can you guys see that or not?
Yeah.
On the second equation, I'm going to do what?
You're gonna minus 5 and minus P.
Yeah, minus 5 and minus P to both sides. So I get T minus P equals 10. And now I have a system of equations lined up, both in standard form. What do you guys want to do?
We're gonna get rid of the
Get rid of the P's?
No, hold on. We're gonna get rid of the T's.
Would it matter if I got rid of the P's?
No, it doesn't.
It doesn't. But T looks pretty easy to get rid of.
Yeah, you just subtract.
I could just subtract, but then we would know we have to subtract a negative, which means you actually are adding. And I think a lot of students are going to get messed up by doing that. So I propose only adding the equations to solve it. And to do that, I can multiply the top equation by negative 1. So I get negative T plus 2P is equal to 10. And add 1. T plus a negative T is gone. P, negative P plus 2P is P equals 20. Jake in the very beginning said 20 and 40. Was he correct? I don't know. Let's see. Currently, Patricia's 20. How old is Tommy? You can plug this into any equation you want, right? Guess which one I'm going to put it in?
Put in the T minus P, yeah.
Yeah, I'm going to put in the T minus P equals 20. So, T minus 20 equals 10. I'm going to add 20. T is actually equal to 30. Now, we just solved a bunch of equations. We didn't actually state anything. We should technically go back and say,
Tommy's age is 30.
Tommy is 30. Pat is 20. Done. Next problem is, Phil is 8 years younger than Bill. 6 years ago, Phil was half as old as Bill is now. How old are they both now? Guys, the key question is, how old are they now? I could also ask you, how old are they going to be in 6 years? How old will they be in 20 years? I could ask you just how old Phil is. I could just ask you how old Bill is. It doesn't matter. I can change this up several hundred different ways. Change the problem just a little bit. I want you guys to try this on your own. Use what we just did, and we'll come back. What are the equations? Well, first of all, even before we get that, we got to set it up, right? We're going to use P for Phil. And we're going to use B for Bill and Phil. Okay. So now, what's our first equation? P equals B minus 8? This is what I heard. Phil is 8 years younger than Bill. So Phil and Bill are not the same age. If I took Bill's age and subtracted 8, I would have Phil's. Could I also take Phil and add 8? Excuse me. Okay, so Phil is 8 years younger than Bill, so Bill minus 8 is Phil. Okay, next one. 6 years ago, Phil was half as old as Bill is now. So, 6 years ago, so Phil 6 years ago, right? Phil 6 years ago is being compared to Bill now. So he's half the age of Bill. So what?
You multiply 2.
So you could put a 2 on the P minus 6. Or could I right away just say half of Bill's age now is what Phil's age was 6 years ago? Okay. I like what Abby said for the fact that she brought the 2 to the other side. What's that? You can divide by 2, but I think it's easier to say multiply by half. Because it's saying it's half as Bill's age. Now, the reason I like what Abby said is because that way, if I multiply both sides by 2, I'll get rid of the fraction. I will not have any fractions in my problem. But guys, those 2 equations are it. So notice, now we're linking things from 6 years ago and current age. That can happen. So how do we solve this? We could use substitution. How about we do that one instead? Normally I say, hey, let's stick with elimination, put it in standard form and cancel the variable out. But do you notice that this one says P equals B minus 8? So I already know what P equals. Could I then just take the B minus 8 and plug it in for P? B minus 8 minus 6 equals 1/2 B. What's B minus 8 minus 6? B minus 14 equals 1/2 B. Now what do I do? Add 14? Okay. If I add 14, that just brings the 14 to the other side, but it becomes positive at least. What else can I do then? How about get the B's all together? So can I subtract 1/2 of B? Sure, why not? What's a B minus 1/2 of B? 1/2 of a B will equal 14. To get B by itself? Not divide by 2, but multiply by 2. So B is equal to? How old are they both now? B actually stands for Bill. Bill is, Bill is 28 years old. Phil, P equals 28 minus 8, which is 20. So Phil is 20 years. Second group of problems are rate problems. Hey guys, if I ask you this question, if distance 1 was to equal distance 2, then the rate 1 times time 1 would have to equal the rate of 2 times time 2. Well, because remember, distance equals rate times time, right? So if the distances are the same, then the rate and the time from one trip should equal the rate and the time of the second trip. They eventually should even out to the exact same distance, yes?
Yes.
You could be going faster on the first trip, but your time would be shorter than the second trip. That makes sense. We both, everyone in this class can have a different rate and time on going from, say, this classroom to the lunchroom, because somebody might go slower than somebody else. Say we can all take the same path, everything. It's just that someone might go faster or slower. We still cover the same distance, but someone who's going slower takes more time, and someone who goes faster uses less time. Okay. So, we also know that if distance 1 plus distance 2 equals k, equals some distance or something done, then r1 t1 plus r2 t2 should also equal that same k. Right? Now, here's the thing. I'm using distance equals rate times time, but distance is not the only thing that can be a rate and a time. I'm seeing water bottles on people's desks. Drinking the water bottle can be something that has a rate and a time. You can have a very fast rate of drinking the water out of the water bottle, which would lower the amount of time it would take you to drink the water. Yes?
No.
And vice versa. If you have a slow drinking rate, therefore the bottle of water will take longer to get rid of. We call these type of problems jobs, or sometimes instead of distance we call them jobs instead. So building houses, baking cookies, or eating cookies can be, instead of a distance, we talk about jobs instead of maybe even K. And then we also can figure that we may have a case or a package of cookies. And by myself, I can eat them so fast. Maybe I can eat 2 cookies per minute. But Jason can eat 4 cookies per minute. Okay? Together, we would be able to eat his 4, my 2 or 3 or whatever it was. So it'd be 6 per minute. But here's the problem. Sometimes we don't start at the same time. Jason maybe starts 3 minutes faster than I do. How long is it going to take to finish the package of cookies when I eventually join him after 3 minutes?
6 minutes.
Okay? So these are going to be types of things. So individuals, there's some assumptions going on here. That individual members will work at the same rate whether they are alone or whether they're with someone else. I know I have first-hand experience with this when I worked at Cub Foods, stocking shelves. If I stocked shelves, I could stock them at a certain rate by myself because I got no one to talk to. I'm just working. But as soon as you threw another person in the aisle with me and we started stocking the shelves together, both of our productivity rates went down because we started talking. Think of when you guys do your homework. When you're doing it by yourself and you understand it, or whatever, right? You're working, you're getting so many problems done in a certain time. But as soon as you bring a friend into this mix, or your phone, your productivity starts to drop. You can't get as much done in the same amount of time. So what we're going to assume is that even if I'm working by myself or working with someone else, my rate will always stay the same. Each member can work their own hours at their own rate, thus completing different number of jobs. So, going back to the cookie example, Jason will eat different cookies or amount of cookies than I'll eat because we have different rates, even though we could go for the exact same amount of time or different times. Okay? We do not have to do everything together. So, sometimes on these problems, especially when we have to start thinking of a problem that looks like in this form where we have people joining together, a lot of the times someone will be already started at the job. Then they will be joined by someone else. And the way I would like to explain it is there's an alone time and then there's together time. Okay? Because when the person's working by themselves, they are chipping away at trying to get that job done, right? You got a package of cookies, I'm eating the cookies, and all of a sudden someone else joins me. We don't start over eating the package again, right? The cookies are gone. The job is already partially done. We just pick up at the next cookie in line and keep going. Make kind of sense? We're not starting over. So, here's the problem that we will have to do. Napoleon walked part of the 60 miles to the site of the battle and rode the rest of the way on a horse. I mean a caisson? Anybody a horse person? Yeah, Bond, you a horse person? You know that?
We actually own like 8 horses.
Okay, good. Do you keep them under tents? Next to the Volkswagen Bug? Okay. He walked, guys, here we go. So there's two things going on. This person, it's a single person, but yet doing two different things that are related to the same job. Like traveling 60 miles. He can walk 3 miles per hour and he can ride at 9 miles per hour. If the total time of the trip was 8 hours, how long did he walk for? So this is definitely a distance equals rate times time, right? You got a distance, you have some rates, you have some times. Unfortunately, it's just not completely walking the whole distance, and it's not completely riding the whole distance. So it's got to be made up of some kind of rate 1 time 1 plus rate 2 time 2 to get a total distance, in this case, d. Now, time 1 and rate 1 will give you a distance that you will cover while walking. Rate 2, time 2 will be the distance that you will ride. Do we know any of these values? Do we know the rate? Or even change this, guys. Change this to, instead of R1, how about RW, TW? Instead of rate 2, call it RR, TR. Walking, riding. Some way to distinguish what you're working with. Do we know RW? Do you know the rate of walking? 3 miles per hour. Do you know the time for walking? Not really. Do you know the rate of riding? How much? So it's 9. Time riding? Total distance? 60. Now wait a minute. That leaves us with a TW and a TR. That's times. But we know something about the connection between times. Don't we? What's the connection?
8 hours.
What's 8 hours?
The journey in itself.
So how do I put that together? The journey takes 8 hours. What's the journey?
The walking and the running.
The walking and the riding. So how do I state that? How do I state that as another equation? TW plus TR will be equal to 8. And there are your two equations and two unknowns. This whole entire lesson is about setting up a system that you have to solve. Notice that this one's already kind of in standard form. What would be the easiest way to solve this?
Multiply by 3.
Which one by 3?
3 or 9.
Not by 3 or 9, but by negative 3 or negative 9. Which one would be easier? I say negative 3. I heard a couple people say it as well. So the bottom one, right? So I get a negative 3TW minus 3TR is equal to a negative 3 times 8. 24. Add them up. 3TW minus 3TW is gone. 9TR plus a negative 3TR. 6 TRs. 60 minus 24 is 60 plus a negative 24. 36. Divide by time of writing is how many hours? 6 hours
So then couldn't you figure out the other
of writing. Which means that you have how many hours of walking?
2 hours of walking?
2 hours of.
Would you, in that circumstance, would you want us to do like
Technically, you can use the second equation, the TW plus TR equals 8. And you can figure that out. Homework, page 181, lesson 25, 1, 6, 9, 12, 27. Have a great day.